time, but we didn't quite have time for. And of course, I think actually the problem is, so the Pi can output on multiple displays. Actually, I'm going to come over here. The Pi can output on multiple displays, but for some reason, I've been having trouble getting it to output to this monitor and the projector simultaneously, even though I had zero trouble with this last year on, I mean, granted, it was a different system over in Goodrich. And then, so okay, that wasn't working. So I got an HDMI splitter that would take one signal and pipe it to multiple outputs, right? And that seems to be intermittently working. So I'm not sure what the deal is there. Anyway, all right, let's get some code working. Hopefully we can do something today. So a couple things I wanted to do, and one of which is related to pointers, is let's make a new example. Oops. Okay, so I think that's all we'll need. Okay, so we'll have our main function, and just for sake of demonstration, let me declare a string and an array of numbers. So okay, so just declared an array and a array of 4 numbers and a string. Okay, great. And we can, of course, print these things. So if we think about, well, what is the pointer to my string or my array, right? Really, what are those things pointing at? Yeah, locations in memory, but it's the location of memory where the thing starts, right? So in the case of the array, it's pointing to the W, and in the case of the string, it's pointing to the W, and in the case of the array, it's pointing to the memory location that stores the 1. Okay, so let's start with the string part of it. Okay, and let's just print. Let's see. Let's do %s. And here, let me make this a little bigger so we can see it. Okay, so we want that, and then I'm going to need to pipe it into, let's see, the yes. This or this? Oh, it's just a quote mark. It's the key to the left of the 1. I don't really need it there, right? I just put it so that the quote would be, or the string would be kind of encapsulated in something. Yeah, that's just me trying to be fancy. Okay, so in this case, let's see, what do we want? I think actually what we want is we want to pass the strings pointer twice, okay? Um, and the reason is that, like, how do you pass a string to the function? Like for printing? Yeah, so it needs a format string. Okay, that's the first bit. Uh, yeah, right, because this tells it that I want to replace that thing, the %s, with a string, okay? But how do I print a string? What do I have to tell it? I can't give it the entire string, but rather, yeah, the location of it, right? The pointer to it, okay? And so this instance of my string should print the string, but then on this one right here, and in fact, let me put a 0x in front of it. What else do I want to know? I want to know, where is this thing, right? Okay, and I want to print it as a 64-bit int, right? Because it's an address. So let's do this, and then let's return 0. All right, so let's run this thing and see what happens. So let me scoochie this over. Um, so I found a program that does, guys know how, like, in Windows you can, or Mac OS, you can drag a window and it'll sort of snap it to half of the screen. So I found something that does that for the Pi window manager, except it's, no, um, it's super deprecated, old, and so it doesn't recognize that there's, of course, the menu bar up at the top, so it doesn't snap everything below the menu bar, which is not the end of the world, but yeah, okay. So let's go to, let's see, documents, examples. We're doing pointers 2. Okay, so let's GCC pointers 2.c output to pointers 2 and hope that I didn't screw anything up. Oh, looks good. Okay, so what do we got? Oh, and here, let me throw a carriage return in just for cleanliness. Okay, good. So I've, in this case, used the pointer to the string in sort of two different ways, right? Once as I was, so really, let's be clear. What is the pointer to this string? It is that number 7FF8, blah, 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 blah. Okay, so why was it printf printed the actual string in the first place, but the number, the address, in the second instance? Yeah, because I use different things in my format string. In the first instance, I use %s to represent that I wanted it to print it as a string, which means, of course, character by character. And then in the second place, I did LX, which meant I wanted to print it in hexadecimal as a 64-bit thing, right, which is what memory addresses are. And so there we go. Okay, does that make sense? Now, how many of you guys are bothered by the fact that I didn't put an ampersand in front of string, my string? Okay, you bothered by that? Okay, why don't I have to put it in front in this instance? Okay, and yes, I know this is a little bit inconsistent, but, or it seems inconsistent, so let's go back here. My string, this is the pointer, okay? It's not like a numeric variable, like if I said, so all right, let me contrast this here. Right. So let's do like that. Okay. So what is just my number? It's the number 1832. If I want to reference the location of the number 1832, what do I have to do? Ampersand my number. Okay. If I want to address a particular value in the string or the array, that's when I use the square brackets with something inside of it, okay? So the first letter of Wabash Always Fights is my string bracket 0, right? That's the actual value of it. Where is that? Okay, normally you'd say, oh, well, I need to put an ampersand here, right? But it's not. It's just my string is the location of it, okay? So that bothers you guys? Yeah, because it does seem a little bit inconsistent. So just out of curiosity, what would happen if we threw an ampersand in front of this? My claim is that we don't need it here because it's a string. Oops. Absolutely nothing. Okay. So why does the memory address keep changing? Or seems like it keeps changing? That's the operating system doing its thing. Okay, just assigning what segment of memory our program gets to access. But whatever, it's just whatever memory address it is. No, it's not so much randomly. It's just that, so this is sort of one thing I've kind of lied about. So these memory addresses, it's not actually in that memory address. Okay, that's sort of a virtual number. And so what the operating system is doing, right, is it's got this 64-bit address space, and the physical location of it and sort of the virtual location of it aren't quite the same, and it's giving us the virtual locations back, and we just sort of have to deal with that. Okay. So yeah, Owen. Yes. Yes. Okay. So let's do that. So let's print here. Oops. Oops. Okay, so what is it I want to print? The location of the number, whatever, is whatever, okay? So here, right, why is it the first instance doesn't have an ampersand in front? It's a number, okay, an int. And an int is a data type that can fit in a register, whereas a string or an array is not. Okay, so that's, I think, really fundamentally the distinction here. All right, so why is there an ampersand? The second one, because I don't want the value of the number, I want its location, okay, wherever it's stored in memory. Okay, does that make sense? Yeah, so, there we go. All right, so do you have to put the ampersand in front of a string or an array? No. If you do, does it break? No. Okay, so the reason that you don't have to put it in front in that instance is because it's not necessary. How else can you refer to a string? You can't refer to it by value. You can only refer to it by its memory location. That's it, right? Whereas an integer, a number, or a float, or a character for that matter, or a Boolean, right? Any of those data types are at most 64 bits wide, and those will fit into registers, so I can pass them by value or by reference. Can go either way. Okay, does that distinction kind of make sense? All right, now this doesn't get to the whole confusion over the asterisk, which let me find a better explanation for that, other than you just do what you have to, because well, for those of you who are coming to my CS colloquium today, there's going to be asterisks all over the place. and it's disgusting. Okay. Um, so really this asterisk thing, I mean, it gets used in two ways, right? One is the multiplication operator. Okay, fine. That's not rocket science. And then the other thing, it's called the dereference operator. And I don't think I've given you guys a very good explanation as to what that means. So let me kind of think of a better way to put it, and I'll deal with that on Thursday. Okay, is that all right? Okay. All right, so then let's do the same thing here for our array. Okay. Well, okay, so we have a bit of an issue here. How do I print an array? Yeah, I have to print it a character at a time. So I can't just put a magical format string thing here and have it spit out the entire string, okay? So let me just say this for right now. The location of the array is, and then here, like before, do I need the ampersand? I don't need it because what is my array? Yeah. Oh, it doesn't matter, but no, I didn't. LLX and LX are the same thing. Yeah. Oh, sure, just for decoration's sake. Okay. All right, so let's run that real quick. All right. So the location of the array is blah. Okay, good. Okay, so to the point that Owen just made, right? How do I print an array as opposed to a string? I need a loop because I have to print it number by number, okay? I couldn't, for example, do something like this. Okay, why won't this work? Okay, because what is my array? Is it a string? No, it's an array of numbers. Okay, so if I run that, okay, right, it's not really going to work. And then, of course, what on earth went on here? That's interesting. Yeah, okay, so this is just garbage, right? Um, and actually, I think this is just two of these numbers sort of shoved together somehow. Okay, so that doesn't work because the array isn't a string, it's an array, all right? And in terms of the data storage, what's the difference between them? Okay, so an array is, in this case, an array of what's? What kind of numbers have I put together in my array? They're the integers, right? How wide is each integer? How many bits does it take to store it? 32 bits, okay? And so if I were to look in memory at whatever that starting address is, in that memory cell, I would see, well, let's do that actually, okay? So let me just delete that because it of course gave us garbage, okay? And recompile it. All right, now one thing I'm gonna do here, is I'm going to statically compile it because I want to then go into the debugging thing. And the static compiling I found makes the printing stuff work a little better in the debugger. Okay. All right, so I'm going to put a breakpoint at line 14. Oh, and I forgot the debugging. Sorry. I also need the -G flag, so it generates the debugging stuff. Okay. All right, so I'm going to put a breakpoint at line 14, which is here, right? So that basically the program will do everything it's going to do and then just pause right before it returns back to the OS. so that we're still in the program technically. All right, and so I'm going to run, and it's going to print all the stuff. Okay, and that all looks good. Okay, good. Yeah. All right, so let's look in memory at these addresses and see what's going on. Okay, so, oops. Well, okay, that's good enough. Okay, so what I've done here is, so $SP stands for the stack pointer, and we'll talk about what that means in a bit. But it's a pointer to memory, okay? And in this case, its value happens to be blah, 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 010. And so I want to sort of think of that as a starting memory address that has stuff that I'm interested in, okay? And what were the addresses we saw when it printed? 24, 28, and 38, okay? Well, if we look at memory address, let's just start at the bottom. What's in memory address 24? Okay, so that's memory address 24 is where? Right. Okay, memory address 24 is contains the number 28. Okay, so the location of the actual number, well, first off, what type of data, what data type was 1832? It was an integer. Okay, so that takes up 32 bits, right? And so the number 1832 is really sitting here in those four memory addresses from 024, 024, 025, 026, and 027, right? So those four memory addresses. And why does it take four memory addresses? Pray tell. It's 32 bits. Okay, because I defined it as an int. If I had defined it as a long int, how many would it have taken up? 64. Okay. All right, now contrast that. Let's look at the location of the array. Where does the array start? What does it say? 028. Okay, so where's 028? Right here. 1, then 8, then 3, and then 2. Okay, so each one takes up how many bytes or bits? Takes up how many? 32, because I defined this as an array of ints. Okay, is that right? All right, now let's look at the string. Where was the string's starting address? 38. Okay. All right, so where's 38? Yeah, so we've got 30333 is here, 34 through 7 is here, 38 through 8, 9, A, and B are in the second column, and C, D, E, and F are in the fourth, the last column. Okay, good. All right, does that look like the correct string data here? Yeah, because what do we got? 5, 7 is, yeah, that's a capital W, right? And that's the location 038, right? And then 039 is the 6-1, the A, B, A, S, H, space, and so on. Okay, so why is it that each character in my string is only taking up 8 bits, whereas each integer in my array was taking up 32? Why, pray tell? Do I need to come beat people with the stick to get the answer out of them? Cole, I'm coming for you. Huh? Well, let's see. Who deserves a stick beating? Who hasn't had a stick beating in a while?
Hopefully all of us.
Oh, okay. He gets a stick beating. He raised his hand. Yeah. Question? Or you're volunteering for the stick beating? Okay. There you go. Okay. 40 lashes with a wet noodle. Okay, so do I need to rephrase the question? Are we clear what the question is? And if not, that's okay. Huh? Yeah, okay. What was the question? Now I'm forgetting. Okay, yes, so it is. Why is it that the string, each character was only 8 bits, and the hex is just a way of representing it, like displaying the data, right? I can make anything be displayed in hex, right? So characters here are 8 bits wide, whereas integers are 32 bits wide. Why is that? Well, how are characters encoded? In ASCII, which is a how many bit scheme? It's an 8-bit scheme, okay? Now, if I were to rearrange everything and do all this in Unicode, okay, or UTF-8 or something, how many bits does it take to represent a single character in Unicode? Well, it depends on which system you use, but more than 8, okay? Well, okay, that's actually a more complicated question. Yeah, up to 32, okay? Um, and now if you think about why is that a good thing, that Unicode might take up more bytes for a single or more bits for a single character. Well, if we use 8 bits per character, how many things are we able to encode? How many different characters? Huh? 4? If I use 8 bits, how many things can I encode? 256. Why 256? What's 2 to the 8th? Right? 2 times 2 times 2 times 2, right? 250, 2 to the 8th is not very big. It's just 256, right? Okay, 256, is that enough to encode basically every kind of character you might want to encode? It is if you're like Western European, because Merca, right? But what about if you're Chinese? Yeah, well, I'm looking to Sebastian. I'm going to let him be the expert on the Chinese language right now. Yeah, you think your Chinese is better than his? Okay. Remind me to teach you the 2 Chinese curse words I know after class. Okay. Yeah, they're really awful. Anyway, okay. So, but how many characters are there in Chinese? Thousands, right? And that's just Chinese, right? Because what else has lots of characters? Well, okay. Now, so Japanese actually is interesting because most of those thousands of characters are actually the same as they are in Chinese. They just have, in some cases, different meanings and are pronounced differently. So the Japanese writing system, and this is kind of interesting, they actually have 3 writing systems. Okay, and they use all 3 simultaneously. Okay, kanji, which is the set of symbols that they learned from the Chinese. Okay, and then 2 sets of symbols called hiragana and katakana, which basically do the same thing, but they use them in different contexts. And those are more like an alphabet in the sense that there's only 50 something of them. Okay, and the reason that there's more than like say 26 or whatever is because those are actually syllabaries, not alphabets. So a syllabary would be like so like in English we have the letter K, and then we have a bunch of vowels, right? So you can make ka, ke, ki, ka, whatever, right? Well, what about if we had different symbols for each combination of a consonant and a vowel? That would be what's called a syllabary, and that's how hiragana and katakana work. Okay, right. So basically, Japanese isn't an issue in that sense because if we've already encoded Chinese, adding another 100 or so is not really a big deal. Okay, but then throw in like, oh, I don't know. What about if you want to put cuneiform characters, or linear asyllabary, or hieroglyphics, right? Well, I think I just, yeah, cuneiform, right? So like Gilgamesh and stuff, right? Or the poop emoji, right? It has its own Unicode character encoding. But you know what's not in Unicode? Klingon. We can have the poop emoji, but not Klingon? That's ridiculous. Well, actually, yeah, that too. So in the 90s, actually, the Klingon Language Institute did submit a proposal to the Unicode Consortium to add Klingon to Unicode, and they rejected it. So, yeah, I think we need to go back and be like, okay, look, guys, like, and that would be the argument, right? We have the poop emoji. Let us have Klingon.
How does emojis?
Okay, so good question. They're not actually like the shape of the poop emoji is not actually encoded in Unicode. No, it's not an image. It's just this number in Unicode is what you use to represent the poop emoji. Now, how the poop emoji looks on your screen is a totally different matter. Yeah, like the Unicode is not a font, if that makes sense. Okay. All right. Anyway, sorry, I've gone off on an arc hyperbolic cotangent.
Sorry.
Yeah, you guys know me.
We're here for it.
Well, okay. So I've done something for the first time in my career at Wabash. How many shots of espresso were in this? Normally three. It's four. No. If I drank the whole thing right now, I would, but yeah. Okay. So my point here is, why is it that the characters are only 8 bits wide versus the integers being 32 bits wide? Because I defined them that way. And because in C, characters are defined in ASCII, and ASCII is an 8-bit system. Okay. Now you might, I'm harping on that for a reason, and we'll see why in a minute. Okay. Question, preguntas, Fragen. Oh, and I've never explained why I say that, do I? Have I? Well, I maybe explained it to some of you guys. So there was a professor here of French, Tom Stokes. He passed away very suddenly in, I think it was 2015, somewhere around there. And I sat in on his French 101 and 102 class. That's how I started learning Parler Français. Anyway, whenever he asked if there were any questions, he would always say question, preguntas, fragen, which is question, question, question in French, Spanish, and German, respectively. And then he passed away suddenly, and I sort of stole it because it reminded me of him. So, yeah, he was, I think the biggest irony of it was he was going to, I think it was Montreal for a conference, or maybe Quebec City, and he was going to present a paper on waiting for Godot, and he just dropped dead from a heart attack on the way to the conference. And so they're all sitting around at the conference waiting for him. And yeah. So anyway, huh? Waiting for Godot is a novel. Yeah. So okay. Questions, preguntas, fragen. Okay. So if I wanted to print the entire the entire array 81832, what would I need to do? Yeah, I need to do a loop or something like that, right? Okay, so let's just set up a loop, okay, to go through it and print each of those numbers, okay, just for funsies. Well, okay. Huh? Size of instead of. Yes, okay. The reason that didn't work is because the size of or the length thing is in well, okay. Well, and that's exactly the issue I want to talk about in a minute. Okay. So in this case, I'm just going to hard code here 4 because I know that my array has 4 characters in it, or 4 numbers, excuse me. Okay, is that all right? And yes, you could make it be dependent on the length, and we'll deal with that in a moment. Okay, and then there. Okay, so what do I need to do here? I want to printf, and let's come up with something. Oops. Okay, so array element number blah is blah. Okay, and I just want to do this, and I'll pass I as the first thing so that I'll see array element number 0, array element number 1, and it'll just sort of display it, okay? And then what is the actual number that I want to print in this case? My array of, oops, bracket I, okay? And that's going to refer to the specific number, the 1, the 8, the 3, or the 2, one of those, okay? All right, does that make sense? Yeah? Okay. Oh, and let's put in a character term, just for good measure. Okay, so let's run this. Okay, does that look correct? Yeah? Okay, 0 is 1, 1 is 8, 2 is 3, and 3 is 2. Okay, good? Yeah. All right, so, um, like this? Yes, it would only print the 8, the 3, and the 2. Okay, because I have skipped over and not done the 0th index. Because of course everything in C is 0 indexed rather than 1 indexed. Sorry, it's just the way it is. 0, I think. I mean, you can index any way you want, right? But well, in the sense that you can count however you want. But if you've got a string and you want to look at the first thing in it, it's that string of 0, not that string of 1. So in that sense, yeah, Python's still 0 indexed, right? I mean, I could have made this I equals 17 to 21 and then just subtracted 17 from I each time. Now, I wouldn't do that because that's like deliberately obfuscating the code, but I could have. I do my array of I minus 17. Right. I mean, that'd be kind of smoking it, but I mean, I could. Yeah. So, and Mr. Powell, I'm just noticing your hat. Did you rush Uzma Kappa? Mhm. He's wearing a Monsters University hat. Yeah. So, okay. So, great. So that printed these things. Now, I want to talk a little bit about the pointer stuff, okay? Because um, what if I did the exact same thing but for my string? Okay? Now, in a sense, right, printf is already doing that when I pass it a string. We're really, all it's doing is printing character by character, right? Okay, so let me, are we good with the array, or sorry, the for loop thing? Okay, do you guys mind if I comment that out just for the moment? Okay, so what I want to show you is this. Well, okay, let me actually comment out this stuff too for just right now. Okay, and I'll just come up here and do it here. So comma, okay. Okay, so here's what I'm going to do. I'm going to take my string, right, which is really a pointer, okay? So the character at blah is this, okay? All right, so what should this do? Should print me the first character as a character, okay? So my string of 0, what does that mean? The first thing that's in my string, okay, which is the capital W, right, as a character. Okay, is that all right? All right, so let's compile and run this. Yes, it's 20, I think. Yeah, but it is in the ASCII table. In fact, we can figure that out, right? We can just look at the string, right? Because we've got W A B A S H space 20. And this actually illustrates what I meant by encoding the character is different from having a font to represent what that looks like. Okay, because how do you represent visually a space? Well, okay, you could, but that's a different character in ASCII. There's nothing there, right? It's sort of the absence of pixels. Yeah, and this, by the way, so it may be a better explanation of this. How many of you guys have iPhones? Okay. How many of you guys have Android devices? Okay. What does the hamburger icon, the hamburger, look like in iOS versus on Android? Well, they don't look the same, right? Okay, but they're still the same. Yeah, but it's still the same Unicode number, right, for the hamburger emoji. Okay, even though on Apple it looks a little different, and they've updated it because, I mean, for example, there was one version where they put the cheese under the patty. I mean, who does that? Just who does that? Well, yeah. How many of you guys put together a hamburger and you put the cheese under the patty rather than? Well, there's that. But thanks, Owen. God. Okay. So good. Yeah. Okay. And if I wanted to go to the next one, what would I do? Let's go with a 1. So this is, okay, survey says, and should I just add 1 to the address? Okay, well, yeah, right? Well, okay, because characters, right, how many bytes do they take up? Or bits? 8 bits, which is 1 byte. Okay. Yes, 2 nibbles. Okay. All right, memory addresses store how much each? Every memory address stores exactly 8 bits, 1 byte. Okay. So if I say my string plus 1, what I'm doing here is what's called pointer arithmetic. Okay. The pointer is a number, right? Can I add to that number? Sure. Right? And what's 1 byte down from the starting memory address of the string? So if I run this, what should I see? The A, okay? The first A. Then it would have a mismatch. We'd have one memory address, the location of one memory address and the location of one character, but they wouldn't be associated with each other. Okay. So here, the address of the character A is whatever. Okay. And it's one address down from the start. Okay. So for example, let's just duplicate this just for now. Oops. Okay, so there. Okay, does that make sense that we're getting the output that we ought to be getting? Yeah? Okay, because what's the location of the W? EO. Okay, and what's the location of the A? E1. And that's 1 byte further down than E0. Fake news. Okay, thanks, Cole. Yeah. Yeah. I've missed having you in class. Wrong phrase. Okay.
What is an integral?
Okay, we good? Yes, AJ. Ajay, excuse me. I'm sorry? I can't hear you. I'm sorry. In Python, what now?
So if you write a equals 2 and then use like a later on, it increases the reference of a in Python in memory to save the memory. Is something like that?
I'm about to do that. Yeah, and okay. Okay, so good. All right, let me show you something that is going to drive you guys bonkers. Let's do the exact same thing. Okay, so I've got a string. I've also got an array, right? If I want to reference the 1 that's in the array, that was the first thing, so it's my array of 0. If I want to reference the 8 that's in the array, it was my array of 1, and so on. Okay, good with that. Okay, so let's just run this. And there they are, the 1 and the 8. That looks good. Oh, I am. I'm just waiting for you guys to notice it. Oh, what the hell is going on there? Keep talking. Keep talking. Howard integers encoded. Huh? 32 bits or 4 bytes. So you see how the addresses are 4 off for the numbers, but only 1 off for the characters? Yeah? That makes sense, right? Okay, here's the part that's going to drive you guys bonkers, though. What did I put there? I put +1, not +4.
I feel like it probably does that so that you don't get confused.
Well, sort of. It's going to confuse you one way or the other, right? So I was able to put +1 here because I'm piping this thing through a compiler. The compiler isn't stupid. The compiler understands that, where are you putting your bag on? You still got 20 minutes, bro. Oh, okay. Normally you tell the professor about this beforehand so he doesn't think that you're just saying, flipping the table and storming out, okay? Okay, so when I said my array +1, why did it really give me what appears to be my array +4? Right, that's the next available memory address to store an integer. Okay, because integers take up 4 bytes, not 1. Okay, does that bother you that the +1, like, you might have thought it should be +4? Not really? It's actually better in some sense. Okay, but in C you aren't. When we're doing this in straight assembly, you will have to add +4. Okay, because, so think of it this way. +1, right, by putting +1 or my array of 1, isn't it nice that the ones match? Yeah, that's kind of nice. You don't have to do the mental gymnastics that you're going to have to do when we do this in straight assembly. Okay, so I've written this thing, and what happens when I compile it? The compiler is going to analyze this thing, and it's going to be like, oh, my array is a pointer to what kind of object? It's a pointer to an array built out of what? Integers. What is the size of an integer in terms of how much data it takes to encode it? 4 bytes or 32 bits, right? And so it's going to be like, oh, when he says 1 here, he really means +4, because that's how many bytes it takes. Yeah. Okay, so this is what I said. This is called pointer arithmetic, right? Pointers are just numbers, right? And that means that I can do arithmetic with them just as I would any other number, okay? But I have to be careful in the sense that I need to make sure that I understand what really is the next thing that I want to point to, okay? Now, just to demonstrate that the compiler is being smart here, okay, let me make one minor change. Well, no, actually, no, forget that. Yeah, okay, so the +1 there means +1 in the sense of what's one integer down, okay? If I were to redefine this here as a long int array, what would I expect to see this time? How far off would it be? 8 off, okay? Because if I define it as a long int array, how many bytes are required to store each long integer, or 64-bit integer? 8 bytes, not 4. Okay, does that make sense? Yeah? Okay. Good? Sort of? Okay. Okay. Well, first off, let me go back and let me just do it as a regular int. Okay, so the question is, what would happen if you put +4 here and a 4 here? Just keep the 1? Okay. Well, okay, so this is still going to print the 8, right? Because that is my array of 1. Okay. Okay, so if I add 4, right, how much does it actually add there? Not 10. No, 16. Yeah, well, okay. It looks like it added 10 because I went from 50 to 60, but you're being a dumbass because 50 is not 50. It's 50 hex. So what's 50 to 60 in hex? That's a difference of 16. Right? Okay, stick beating for you on the way out. Oh, also, Mr. Powell, find him 1 gentleman coin. Okay. Really? Man. Yeah. What did you do to be minus 100 gentleman coin? He spoke out against the state. Okay. Well, as I explained to you, at least with respect to this class, l'état c'est moi. Right? No, do you guys know that? Louis the 15th or 16th, the state. I am the state. Right? Yeah. Yeah, well, he kind of lost his head over it. Or Louis the 14th, one of them. A lot of them lost their heads, literally. Okay. Okay, where the hell is my coffee? There it is. Okay. I need to like put an air tag on it, or like have it like a little beep transponder thing, so I could just echolocate to my coffee. Right. Okay. Now, to be clear to Cam's question, is the location of the 8060? No, it's actually 054. Okay. But it printed 060 because he asked me to put a +4 there rather than a +1. Okay. So, yeah. Okay. So the compiler is being nice to you. When we do this in assembly, you're going to have to know that if you're going through an array of characters, character by character, you can go off by, you're off by 1 each time. Whereas if you go through an array of numbers, you have to make sure to skip the appropriate number of memory addresses as you go along. Okay. And see, right, the compiler has dealt with that problem for you, but eventually the compiler goes away, right? That's the whole point of this class. Okay, good. All right, so let's start to talk a little bit about what assembly is and what it means. Okay, so let me, just because it's going to drive me crazy otherwise, let me put that back the way it's supposed to be. Okay, and let me go into GDB and then, okay, line 29 is the one I want to break at. Okay, so the way that a processor actually executes instructions, okay, so well, okay, let me start here. Let me start actually by let's go down to here. So the way that a computer is going to execute code, right, is so data and programs are just things stored in memory, okay? And so let me back up here. Let me think of memory as just being a bunch of little mailboxes, okay? And I'm going to hand the processor, okay, the processor has a register in it that is called the program counter. Okay, sometimes it's also called the instruction pointer for reasons that'll become clear in a minute. Okay, and that's a mailbox number. Okay, and then I'm going to say, processor, make your program counter this mailbox number. Okay, so the processor is going to say, all right, great. It's going to go to that location in memory, and it's going to pull in however much data, and it's going to be like, ah, this is an instruction. I'm supposed to do something. Well, what does that instruction mean? Well, depends on what it is. So it has to decode the instruction and figure out, well, what does it mean? What is this instruction telling me to do? And then it has to do it. Okay? Is that all right? Well, so then what comes next? What should the program counter do after it's loaded in this instruction and done it? It should increment to wherever the next mailbox that would have an instruction would be. Okay? And it's going to continue that process until one of two things happens. It comes to an instruction that tells it to halt. Okay, so some processors have a halt instruction. Okay, or our program would terminate in the sense of like when we return 0, that returns the processor or the program counter back to what it was before we started our program. Okay, so that's sort of returning control back to the operating system. Okay, now, here's what's nice about ARM assembly, okay? So the instructions, when I say the instructions, what the processor is actually reading is this stuff here. Okay, does that mean anything to us as humans? The FD7B blah, blah, blah. No, I have no idea what any of that stuff means, okay? That's an instruction encoded 32 bits, okay? And the encoding for these things is part of the ARM architecture, okay? And we could go look up all the encodings for these things. Now, what does this mean to me as a human? Well, it means STP-X29-X30-SP-64 exclamation mark. Okay, now that doesn't mean anything to you guys right now, but it will eventually. Okay, that's an instruction. Okay, and so what would happen is the program counter starts off at whatever the memory address where this stuff is stored. Okay, so let's think of that like in memory, it's going to be someplace. And let's think of that place as being the base address, okay? And it could be like when we were printing out some of these characters and stuff, you know, 7FFFF, blah, 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 blah. Okay, so that's someplace, right? And so let's think of this set of numbers here, the 4 zeros, the 0, 4, 8, and so on, as being offsets from that. Okay, so what is one instruction? I load in the instruction. I just loaded in 32 bits worth of stuff. Okay, and then I need to decode it, figure out what it means to do it. Okay, and then I need to increment my program counter to the location of the next instruction. Well, what is the next instruction in this case? FD030091, okay, whatever that is, right? That's an instruction. What does it mean? Move X29, comma, stack pointer. Okay, what does that do? That's another matter. We'll talk about that later. Okay, but point is, it's going to load in the next instruction, decode it, and execute it. And then after that, what does it do? Next instruction, next instruction, next instruction. Okay, so the program counter in sort of most cases is just going to increment each time you come through an instruction. And the beauty of the ARM architecture is that how much does it increment by each time? 4 bytes, 32 bits. Okay, yes. Yes, and that's of course the one caveat to what I just said. Okay, is conditional instructions, because those mess with the program counter, and that's how they work. Okay, we'll get there. Okay, so the program counter, like I said, is just going to load in an instruction from memory. Okay, then the processor has to decode it, then it has to execute it and do whatever it is to do it, and then increment the program counter, load in the next instruction, and just continue this game until the program's done. Okay? All right, now, like I said, what's beautiful to me about the ARM instruction set, and it's not the only one that has this property, what's the length of every instruction? How big is each instruction? 32 bits or 8 bytes, right? It's, sorry, 32 bits is 4 bytes. It's 8 nibbles, right? Because each hex character is a nibble, or 4 bits, excuse me. Okay, now there's nothing special about the number 32 bits, okay? What's beautiful is that they're all the same, I think, okay? This makes architecturally some things easier, and the things it makes easier we can't really talk about until like the end of the semester when we're doing sort of circuit level kind of stuff, okay? Intel's architecture, okay, and for that matter, well, actually, let me show you a classic. What's my favorite architecture? You guys should know the answer to this question by now. Yeah, the 6502. Well, actually, you know what? Let me do it this way. Well, no, I can't, because I've used print statements. 1982, same year I came out, so to speak. Okay, so let me show you this just for sake of quick demonstration. Okay, right? This was computing in the 1980s. Behold, it's 16 different colors, and it's 320 by 200 resolution screen. Yeah? Huh? 1982, right? Yes, okay, and that's because it's in 6502 assembly, and you barely know any assembly, much less 6502. All right, let me blow this up a little bit so it's easier to see. Okay, so here's what I want to sort of look at just a moment. You see there, we have basically the same kind of thing that we do from our listing file that we were looking at a second ago. Okay, 8025, okay, is the location of memory of the first instruction in this particular program. And what is the instruction? 7-8. Okay, great. What's the next instruction? Yeah. Okay, and it's 1 byte down, but then what's after it? An instruction 8C20D0. Okay, how many bits wide is that thing? Yeah, okay. So every instruction in this particular architecture is either 1, 2, or 3 bytes wide, but they're not all the same. Okay, that means the decoding part of the instruction, you kind of have to decode as you go, because as you're loading in byte at a time, you have to say, well, have I hit the end of an instruction yet? Okay, it makes your decoder a little bit more complicated. Okay, the ARM instruction set has every single instruction being 32 bits wide. Okay, they're all the same. That's kind of nice. All right, what would be, do you think, the advantage of having instructions having variable length? The disadvantage is that it's a pain to decode them. Okay, the advantage is, any thoughts? Optimized in what sense? Yeah, okay. It's space optimized. Okay, so while yes, the decoding is a bit more of a pain, okay, the amount of memory that it takes to store the program is reduced. Okay, because there's no need to spend 32 bits encoding something that we can get away with only 8, say. Okay, is that all right? Now, let's think about this. So this processor, right, that this is running on, the 6502, right? It was, 1970s era processor. Okay, it's very simple. It has 3,000 something transistors in it. Not particularly complicated. Okay, but for example, the machine that this is emulating, the old Commodore 64, my favorite. How much memory did this thing have? Not much, by modern standards. How much memory? 64 kilobytes. Okay, and that's not a whole lot of memory, is it? Okay, so back then, having an architecture that minimized the amount of memory you needed to store a program was a good thing. Okay, Intel's architecture of the day is similar. Okay, in the sense that each instruction is not the same width necessarily. Okay, now flash forward to today, and so let me finish this and then we'll quit. Intel's architecture today, when you guys did the cross compiling and stuff like that, did you actually open up the listing file for the Intel version and look at it? Okay, what did you see in terms of the instruction lengths? They were variable. Okay, it's still Intel, or at least x86. So Intel's architecture, like this is what's freaky, right? These laptops, all of the ones here in this room, have Intel chips in them, right? Or maybe it's AMD, but it's still Intel architecture, okay? Can you run code on them that was written in the 1970s? A byte code, meaning like actual machine instructions. Yes, you can, okay? This is one of the reasons that Intel had such a competitive advantage, because when they came out with the 486 processor or the Pentium processor or whatever, it could still run all the shit that you were running before, right? You didn't have to recode all of your stuff. Okay, so it has backwards compatibility. That's nice, but it comes at a price. Namely, your instruction set just gets ludicrously complicated. Okay, and to give you an example of just what the price is, okay, so Apple, right? What are the processors in all of their mobile tablets, phones, watches? They're all ARM architecture, and they're actually switching to that on their computers too. Okay, so the M1 chips in the MacBook Pro and Air and Mac Mini, and then they're going to fill out the rest of the product line here in the next year or so, are all running custom Apple designed ARM architecture chips. Okay, now this presents a problem for Apple because they've been previously using Intel. So what are they going to do for their customers so that their customers can run all of their Intel crap before the developers of that stuff update it to take advantage of the new chips? Well, they wrote a compatibility, a translation layer, okay? So that an ARM chip could basically pretend that it's running Intel stuff. Here's what's freaky. In benchmarking, an ARM, an M1 chip could emulate x86 instructions and execute them faster than an x86 chip could do it natively. Right? That's insane. Right? And so this is sort of how you know that Intel's kind of, in a sense, hit an architectural dead end. Well, yeah, that's a whole other matter. So, okay. All right. So we're going to start talking about assembly and getting into the weeds of this stuff with the one exception. Okay, actually, I guess Thursday, there's two things I still need to do. We need to really demystify this whole asterisk thing. And I want to talk about structs. Okay. So compound data objects in C. All right. And we'll talk about that Thursday. And then I guess Tuesday next week, we'll start the assembly. All right. Thanks for playing. See you guys later.